In this episode of Bite Scized, we're going to explore a way that we can represent covalent bonds and molecules through models of atoms called Lewis structures. You probably have seen models of atoms before, like this Bohr model. A Lewis structure is simply another model of the atom. It's just one that focuses on valence electrons. You might also see these called a variety of things like Lewis structures, Lewis dot diagrams, or Lewis models. Generally, Lewis structures are really helpful for thinking about covalent bonds and how electrons are distributed throughout a molecule. Before we get to molecules, let's look at Lewis structures within a single atom. So the first step is we need a periodic table to determine the number of valence electrons in that atom. If that's not super familiar to you, we recommend pausing here, going over that, and then coming back to this. So I'm going to draw the Lewis structure of all of the elements in the second row. I think it's actually easiest to start with neon, which has the most valence electrons, and then go back. So to start with drawing a model of neon, we'll start with its symbol, and then draw dots around it to represent its valence electrons. So for neon, we have 8. Fluorine has 7, oxygen has 6, nitrogen 5, carbon 4, boron 3, beryllium 2, and lithium 1. Now, before we go any further, it's actually helpful to understand who developed these and why. These structures were developed by an American chemist, Gilbert Lewis, in 1916, and he used these to explain the role of valence electrons in covalent bonding. And he had 2 rules. First, a covalent bond was formed between atoms when they share a pair of valence electrons. Second, atoms were combined in ways so they had 8 valence electrons. Sometimes we call this a full shell. Now, there are some exceptions to this rule. For example, hydrogen and helium atoms only need 2 valence electrons to have a, quote, full shell. While helium is a pretty uncommon atom, hydrogen is super common. You're going to see it in all types of molecules. So that's a really important exception to take note of. So for example, if we have hydrogen gas, or H2, we have 2 hydrogen atoms bonded together, which we can represent through this line. According to Lewis, this bond means that they are sharing a pair of valence electrons, or 2 valence electrons. So this is another way we could represent it. In this example, we're also going to look at chlorine gas, Cl2, simply because hydrogen is an exception to this rule. So if we go back to the periodic table and look at how many valence electrons each one of these atoms has on their own, we'll see that hydrogen has 1 and chlorine has 7. We're going to focus on chlorine right now. Now, if we focus on just one atom, one of those valence electrons is already present in the bond, meaning it has 6 left over, which we can draw around that atom. We can now count the total number of valence electrons surrounding that atom, and we'll notice it's 8. It has 7 of its own, and then an additional 1 that is being shared from the other atom. Looking at the other atom in this molecule, we can see the same exact thing mirrored for that atom. We can do the same thing for hydrogen. It's just much simpler because each only has 1 valence electron, and they only need 1 more to have a full outer shell. Now, just to clarify, these are not Lewis structures because, well, this would actually take a lot of time to write out for a larger molecule, and kind of the whole point of this model is to have a quick and easy way to represent valence electrons. However, we think it's helpful, so when you actually look at the final Lewis structure, like you see here, you understand how it was developed. To recap, when we have a bond, which is a pair of valence electrons, we represent that through a line. And then we show the other valence electrons through dots. So let's look at a slightly more complex molecule, OF2, and while we make a Lewis diagram for that molecule, we're also going to outline some basic steps that you could use for other molecules. So the first step is to identify the total number of valence electrons that are being distributed throughout the molecule. We can do this by using the periodic table and identifying how many valence electrons each atom has. So we know that oxygen has 6 and fluorine has 7. But we also have to account for the number of atoms. So we have 2 fluorine atoms. So we're going to take 6 plus 2 times 7, which would give us 20 total valence electrons. We're actually drawing out each valence electron to show you all 20, but we don't recommend actually doing that. It's just to help you visualize what's going on and how we're building out this model. Step 2 is identifying the central atom in the molecule. and it's always going to be the atom that has the lowest electronegativity. So this is where it's helpful, again, to have that periodic table. In this case, oxygen has the lowest electronegativity, so it will be in the middle, and we're going to place the fluorine atoms around it. Next, we're going to draw the bonds between those atoms. So we'll draw a dash to represent the bond between each fluorine atom and oxygen, and we'll calculate the number of valence electrons present in those bonds, which would be 2 pairs of valence electrons or 4 total. Our next step is adding some of the remaining valence electrons to the outside atoms in order to fill their shell. So each one of these fluorine atoms needs 8. So we can draw 6 more valence electrons around these atoms. And then we can subtract that from our total number of valence electrons. So now we have 4 left. The next step is to place those remaining electrons around the central atom. Now we're going to check and look at the central atom and see how many valence electrons are surrounding it. If we have 8 or more, we are good to go and our model is done. Otherwise, we need to reassess things. Now, that's a pretty simple one. It might not always work out that way. We might not actually have enough valence electrons to place around the central atom, in which case we would probably have to go to double or triple bonds, which we're not going to cover in this video right now. We hope you found this video helpful, and be sure to like and subscribe for more videos.